3, and we're on our second day of trig. Yesterday we talked about right angle triangles and the tools that we have when solving for angles and sides. SOHCAHTOA is our most pressing, but we also have Pythagorean theorem. So you have this cheat sheet in your notes, and today we're going to try and solve some real life problems that involve right angle triangles. So first order of business is to, oh, that was a joke from yesterday, is to remind you about angles of elevation and angles of depression. I don't think this is in your notes. It wouldn't be a bad idea to just make a note of those two words that we use often when solving trig problems. So the first one is an angle of depression. Saddest puppy I could find. So an angle of depression is when you look out horizontally first and then look down in a sad sort of a way. So this would be an angle of depression when you look from horizontal downwards. An angle of elevation is horizontal first and then upwards in a happy sort of way. There's an angle of elevation, horizontal first and then upwards. Okay, the first word problem we're going to solve involves an angle of depression. Okay. A hot air balloon on the end of a taut 95-meter rope rises from its platform. Sam, who is in the basket, estimates that the rope and the stake to which it is tied form an angle of depression of about 55 degrees. How far did the balloon drift horizontally, and how high is the balloon above the ground? Well, the first thing we need to do is to draw a picture. And so here we go with a balloon. Okay, hot air balloon. And it has a basket. Oh, he's crooked. There's a basket. And it has Sam in it. Of course, Sam is afraid because it's such a crooked basket. Ah! All right. It is tied to a taut 95-meter rope. It is tied. It is 95 meters. All right, so Sam says that there's an angle of depression with this rope and the stake to which it is tied of about 55 degrees. So we know an angle of depression would be horizontal first and then downwards. So his angle of depression, and he's depressed because he's afraid of this crooked balloon, is 55 degrees. Okay, so more or less, we have formed a right angle triangle. So let's just draw in our triangle. We can assume that line of sight from the horizontal straight down would form a right angle triangle. That would give us the height of Sam, so I could have drawn the triangle on the other side. And we want to find out that distance along the ground. I'm going to call it x, because why not? It would be the same as the distance up here. So either place you can draw your triangle, it won't matter. Let's get rid of him. Okay, we want to solve these things. So my thought process is, can I use Pythagorean theorem? I only have one length, so no, I cannot use Pythagorean theorem. So I need to use SOHCAHTOA. And for the A question, I want to find the length of x. Okay. So I'm going to write it in my triangle that has a blue and dotted lines. If I want to find x and I have the 95, I need to decide which of those three trig ratios would work. I have the angle 55 degrees. I'm going to label my sides: opposite, adjacent, and hypotenuse. The hypotenuse is always the longest side across from the 90 degrees. So there it is. The opposite side is as far away from the 55 as I can go. Come on, be good. over here. Opposite side, adjacent side, is the one just above the 55 degrees. So I want adjacent. I have hypotenuse. At this moment, I don't care about opposite. So adjacent and hypotenuse sides, I would need to use the cosine ratio. So I always set it up the same. Cos of the angle equals adjacent over hypotenuse. So for this problem, I have cos 55 equals, the adjacent is the x, and hypotenuse is the 95. So to solve for x, I need to multiply both sides by 95. 95 cos 55 equals x. You can show that step times both sides by 95 if that is helpful to you. And then the 95 and the 95 would divide out to 1. All right, so in my calculator, I need to make sure that it is in degree mode, particularly if you're using the graphing calculators. They default to radians. Put it in degree mode and 95 times cos 55. I get 54.5. So the balloon has traveled a horizontal distance of 54.5 meters. So that's A. Part B. How high is the balloon above the ground? For part B, I want to solve for H. So I have already labeled my sides with that 55 degrees. This time I want the opposite side. Since I have the hypotenuse as 95 and I want the opposite side, this time I'm going to use sine to solve. So sine of my angle equals opposite over hypotenuse. Sine of 55 degrees equals, opposite is that height I want to solve for, and 95 meters is my hypotenuse. Same thing as last time. To get rid of divide by 95, I multiply both sides by 95. 95 times sine 55 will be 77.8 meters high. All right, let's try a second problem. A wheelchair ramp is safe to use if it has a minimum slope of 1/12 and a maximum slope of 1/5. What are the minimum and maximum angles of elevation to the top of such a ramp? Round your answers to the nearest degree. So let's talk about the smallest that a wheelchair ramp can be. Seems a little strange to me that it has a minimum slope and then the maximum. So I'm going to draw it with a very shallow slope. So if we have our wheelchair ramp and it has a slope of 1/12, that reminds me of grade 9 where we talk about rise over run. So if you have a slope of 1/12, your rise and your run would be 1 to 12. Implied, vertical and horizontal, I can assume that that is 90 degrees. I want to know what the angle of elevation. So angle of elevation is from the horizontal upwards. So that is the angle I want right there. So I can't use Pythagorean theorem because I don't want to know that other length. I want to know an angle. So again, I'm going to use SOHCAHTOA. I'm going to label my sides with that angle as the key angle of reference. My hypotenuse side is always across from the 90 degrees, the longest side. This 1 is opposite, and therefore the 12 is adjacent, which means beside. The trig ratio I want to use uses the 1 and the 12, which would be O and A. So this time I am going to use the tangent ratio. Tan of the angle equals opposite over adjacent. So for this one, tan of theta. I call it theta. You could call it something else like x or whatever. When I don't know an angle, I always call it theta. Greek letter. Opposite and adjacent would be 1 over 12. So as we practiced yesterday, to find an angle, I need to get rid of that word tan. So to do the opposite of tanning something, I inverse tan. So on your calculator, you do second function tan, gives you that, inverse tan of 1/12. So if you type it in as bracket, 1 divided by 12 bracket, you'll have the fraction 1/12. And our angle in degrees is approximately 4.76 degrees. All right, the maximum the wheelchair ramp can be is steeper. Okay, I made it a little ridiculous there. Okay, and its rise over run would be 1 over 5. So yeah, absolutely ridiculous drawing, but we get the idea. If I want to know that angle, it would be the same idea. Label the sides. Hypotenuse, this would be opposite and adjacent. I have opposite and adjacent, so I'm going to use tan again. Tan of the angle is opposite over adjacent. Tan of theta is 1 over 5. So this time I'm doing second function tan of 1/5. And the angle, second function tan, is 11.3 degrees. So the wheelchair ramp can have an angle of elevation between 4.76 degrees and 11.3 degrees. Okay, another problem. A surveyor stands at point S and uses a laser transit and marking pole to sight 2 corners A and B on one side of a rectangular lot. I don't know if you've seen surveyors downtown Listowel. They're looking through a little sight device, and they're marking off property lines or distances and angles and so on when they're marking properties. So the surveyor marks a reference point P on the line AB so that the line from P to S is perpendicular to AB. So it's starting to get really confusing. We have a rectangular lot, and we have Buddy standing at a point S, and we don't actually know where that is, so let's put it there. Okay, and he uses a laser transit marking pole, so we can assume some accuracy to sight 2 corners A and B on one side of the rectangular lot. The surveyor marks a reference point P on the line AB, so he finds P directly across from him, and he says that it is perpendicular to AB. So this line of sight that his eyes are looking at is perpendicular to that line. Okay. Corner A is 150 meters away from S. And this would be perpendicular as well. And 34 degrees east of P. Okay, so I got my east and my west backwards because I didn't read that part quickly. So corner A is 150 meters away from S and 34 degrees east. So 34 degrees if this were east over here. Okay, I'm going to draw a better diagram. We have a rectangular lot with S somewhere in the middle of the lot. We have east over here and west over here because that's how we usually draw diagrams. So point A is on this corner, B is on this corner. and we found a point P in between A and B that is perpendicular to S, where A is 150 meters from S and 34 degrees east there. B, let's see, 374. B is 347 meters away from S. And it is 69 degrees west of P. There we go. Notice that it is not to scale. My 347 should be much longer than my 150, but I didn't really know where Buddy was standing till I got started drawing it. I want to know the length of AB. So this is what I'm required to find from this point to this point. I would like to know that distance. So what I see is that I have two right angle triangles. If I could find this distance, I'll call it x, from B to P, and I find the distance from P to A, I could find the total distance, x plus y. So let's do one triangle at a time. To find the length A, x, let's not add any more letters. To determine the length of x, I am going to look at this triangle and say, all right, my 69 degrees is my angle of reference. My hypotenuse side would be the 347. My opposite side would be the x, and my adjacent side is the dotted line. I don't need to know the length of the adjacent side, so I want to know the trig ratio that uses opposite and adjacent. That's the sine ratio. So I'm going to set up a sine ratio for the left triangle. Sine of 69 degrees equals opposite over hypotenuse. For this one, that is x over 347. To solve for x, I'm going to multiply both sides by 347 times sine 69. Okay, still checking that it's in degree mode. 47 times sine 69 is approximately 324. I also want to determine the length of y. So for y, angle of 34 degrees is my angle of reference. My 150 is the hypotenuse side. The opposite to 34 is the y, and the adjacent side is also the dotted line for this one. I want to know the opposite. I have the hypotenuse, so I use the sine ratio again. Sine of 34 degrees for this triangle equals y over 150. I'm going to multiply both sides by 150, and I'll have a length for y. I didn't need approximately equal to that last time. 150 times sine 34 this time is approximately equal to 84. I'm just checking my units. Is in meters. Meters. What is the length of the rectangular lot? Therefore, the length of the rectangular lot from A to B, 84 plus 324, which is 408 meters long. Karen is a photographer taking a picture of the Burlington Skyway Bridge, and I cannot think of a place I hate to drive more in this world. She is in a helicopter hovering 720 meters above the bridge and exactly 1 kilometer horizontally from the west end of the bridge. The Skyway spans a distance of 2,650 meters from east to west. If Karen's camera has a wide-angle lens that can capture 150 degrees, can she get the whole bridge in one shot? So let's draw the Burlington Skyway Bridge, and we're going to make it less fearsome than it actually is. There is our bridge. And for the sake of this problem, it says that it goes 2,650 meters from east to west. So we're just going to pretend that the distance we're working with here is just flat. So I'm going to use that dotted line because that's the east-west distance. So it's west this way, east this way. Okay. So Karen is 720 meters above the bridge. So she is up in the sky. There. I'm not even gonna oh yes I will, come on. So we have a helicopter, he's got, oh this is dreadful. Big, huge. Okay. Anyway, there's our helicopter. She is 720 meters above the bridge and exactly 1 kilometer horizontally from the west end. So 1 kilometer in meters would be 1,000 meters. So this is this side of the bridge. Okay? We want to know if this 150 degrees can get the whole bridge in one shot. So let's work with this left triangle first and see how many degrees her lens requires to take the 1,000 meters in. So I want to find this part of the angle and see how many degrees we'll swipe that portion of the triangle. If we know 720 meters and 1,000 meters, I need to use SOHCAHTOA to find that angle. The hypotenuse is this line of sight. We don't care about that, but the 1,000 meters is opposite and the 720 meters is adjacent. So how many degrees is she spanning to see that portion of the bridge? We're going to use the tangent ratio. Tan of the angle is opposite over adjacent. So to find that angle, I am going to use 1,000 over 720. If I want to find an angle, I have to get rid of the function tan. The opposite of tan is inverse tan. So shift tan on your calculator. If you put 1,000 divided by 720 in brackets, it can save some errors. And my angle is divided by 720. 54 degrees. Okay, so 54 degrees will allow her to span that 1,000 meters. She needs to be able to see the rest of the bridge. So to see the rest of the bridge, which is, my colors are getting confusing, I'm sorry, is 1,650 more meters. Still a rise of 720 meters high. I'd like to know this angle. I'm going to call it a different Greek letter. I'm going to call it alpha. I want to find angle alpha to see if she can see all of the rest of the bridge. We'll see that angle alpha is less than 96 degrees. Okay. I have opposite for that triangle is the 1650. Adjacent is the 720 again. So I'm going to use tan again. Tan for angle alpha is opposite over adjacent, 1650 over 720. My alpha is inverse tan to find an angle. 1650 divided by 720. Angle alpha . 66 degrees. So in total, she needs to be able to see 54 degrees and 66 degrees. which is a total of 120 degrees. Her camera has a 150 degree span. She'll be just fine.